Welcome back, everyone, for the second part of the FlashCoin Flash white paper, which was released in 2018. Into one of the parts that I think is most important about this white paper and one of the best innovations that the Flash network has implemented, which is network idling. In the earlier years of any cryptocurrency, reading from the white paper here, in the earlier years of any cryptocurrency network, there may be long periods of zero transaction activity. As Layer 2 adoption grows, that will also decrease the level of on-chain activity required for Layer 2 supporting networks. In order to avoid the senseless creation of empty or useless blocks, the new Flash network supports idling, which I think is a fantastic way to go about not wasting blocks and creating, it's like more or less busy work for the network. All incentives for miners to mine blocks as fast as possible have been removed, and the end-chain work no longer exists, so the network can simply stop creating blocks when there is no longer a need for them. A good deal of bandwidth and index space is saved by idling, and it also keeps blockchain syncing as efficient as possible. In order for the network to idle without negatively affecting users, the miners must continue mining blocks at the normal 5-second rate until there are no transactions above consensus height. If the network is idle and a single transaction is broadcasted, the miners will begin mining blocks immediately, and they will continue for approximately 13 blocks until that transaction has reached full consensus. After that, the miners will go idle again until the next time a valid transaction is broadcasted. So this is going to keep the network running more efficiently than, or it keeps the network running more efficiently than a lot of other blockchains that have wasted, wasting network computing power and stuff. Miner and delegate reward mechanics. Every day will start with a transaction that distributes earnings to miners and delegates. Earnings are derived from the network transaction fees. All fees over the last day are added up, split in half, so that 50% go to miners, 50% go to delegates, and then they are allocated as described below. The 50% for delegates is allocated based on each delegate's vote weight at the time of the reward transaction's creation. The greater the vote weight of a delegate, the greater their share of reward. The 50% for miners is allocated equally across elected miners. Foundation rewards. The Third Millennium Foundation pledges to donate 32,000 Flash to the miners and delegates every day in the form of transaction fees. This will be done by using the automated process to send one transaction a day from the Flash Foundation's wallet with a 32,000 transaction fee. These donations will use some expiration date. Voting related opcodes. The voting system requires sending signed voting metadata on the blockchain for all users to see. In order to maintain backwards compatibility with all tools built for Bitcoin, this metadata is sent using the standard op-return Bitcoin opcode and the script of zero-value transaction output. Bitcoin tools do not parse op-return data, nor is this data stored in memory, only on disk. Flash implements several new voting opcodes, which are only used after the op-return opcode. All these new opcodes tell the parser how to interpret the metadata, provide a list of the new opcodes, and you can check these out in the white paper yourself. To the special election address. This is a valid Flash address which has special rules for both receiving and sending transactions. Coins being staked for delegates are sent to this address as is delegate registration information. All transactions into and out of this address must pay the normal network transaction fees. No one will ever know the private key for this address, and even if it were somehow derived, the network only allows coins controlled by this address to be returned to the specified return address or the original sender, so they cannot be stolen. Receiving rules. There can only be there can be one or more transaction inputs. If there is more than one input, a return address must be specified in the voting metadata. The first opreg DG for any given delegate ID must send at least 1 million flash to this address. Any additional stake must be at least 100,000 flash. If there is one transaction output, then it must be the opreg DG operation that is updating any existing delegate. If there are two transaction outputs, then the second must send the coins being staked to the special election address, and the first output must be op stake DG operation adding to the existing delegate stake on the opreg DG operation that is registering a new delegate. Operation specific metadata is provided after the opcode. That's sort of some technical stuff that you probably need to read on your own, but I'm just going through this, trying to hit all of the main points. Sending rules. Anyone can spend these coins without special election address, private key. All transactions received by this address have a delegate ID that are being staked for. That delegate ID must not be a currently elected delegate. Coin staked for the delegate can only be reclaimed if that delegate did not win the election or they have completed their withdrawal from office. For each transaction input being spent, the output address must match the return address in the input's corresponding metadata, or if not provided, then the output address must match the original sending address returned to sender. Special voting address. This is a valid flash address which has special rules for receiving transaction and rejects all sending transactions. When a delegate casts a vote, they send a transaction to this address with the vote data, and they pay a transaction fee for sending the transaction. No coin is ever deposited in this address. It is simply used to make it easier to account for votes. Monitoring this address will effectively monitor all votes by delegates. Receiving rules. There can only be one output transaction which uses the op return opcode followed by the opdg vote opcode and data. The opdg vote data must validate successfully. Sending rules. No transactions sent to this address can ever be spent. The opcode DG vote is explained in a later section, as are the details relating to how a delegate casts votes and how the votes are counted. To the delegate public key. Explanation of the fields. This is the full public key that identifies the delegate. All future actions taken by this delegate will be signed with this public key's corresponding private key. Info version. This is a number that is incremented with every update of the delegate's registration form to ensure proper state. Without this, any delays in transaction replication or chain reorgs must cause an older version to overwrite a newer version. Display name. This is intended to help a human readable string that will appear in various user interfaces for identifying this delegate in addition to the delegate ID. Enabled. If set to true, then this delegate ID will be eligible for return. If set to false, then it will not be. When an elected delegate wishes to withdraw from their duties, then they must set this to false and await the end of the current election term, and then they can reclaim their stake coin. Mining. When set to true, then this delegate is signaling that they want to be a miner, so they become eligible for election as a miner. If set to false, then this delegate is not eligible. If this delegate is already an elected miner, they can set this field to false to withdraw from mining. If registering as a potential miner, then a minimum of 2 million flash must be staked. Audit URL. This is the URL which exposes the delegate's audit interface. There is a new API command which, when queried, returns information that can be used to prove this node is alive and to measure certain performance characteristics. It is recommended that this service, like Memcache, be used when hosting this URL to shield the node from excessive queries. Auditing is explained in further detail in a later section of this document. Contacts. This is a JSON array which contains a list of contact objects. Each object specifies the type of contact address being provided in the address itself. This is intended to provide a way for the community to contact the owner of this delegate. This is optional, however, the community is unlikely to vote for a delegate that they know nothing about. Website. This is a URL linking to the website that represents the delegate or the organization that owns the delegate. This is optional, however, the community is unlikely to vote for a delegate they know nothing about. Pretty obvious. Delegate SIG. This registration form can be sent from any address. It doesn't have to be from the delegate directly. However, the reg data JSON object must be signed with a private key corresponding to the delegate pub key, and that signature must be placed in the field. When the registration data is received and the delegate ID is generated by converting the delegate public key into a flash address. Staking for delegates. Any address may contribute stake to any delegate. However, no coins may be staked for any delegate that has not registered. And the first registration must include at least 1 million flash stake. The first registration stake may be included with the registration transaction, but further stake contributions can be provided by sending the coins to special election address with opstake DG opcode. The staking transaction must have two outputs, with the second sending the coin to be staked to the special election address, minimum 100,000 flash, and the first output must have 0 value in the use return opcode followed by the opstake GG opcode, followed by the delegate ID being staked for, and optionally followed by the return address for the staked funds. If no return address is specified, then the funds can only be returned to sender. Example: op return opcode or op return op stake DG delegate ID return address. It should be noted that these stake coins will not be able to be returned until the delegate they are being staked for has withdrawn from the office and has ended their current election term. To stake coins for a delegate is to surrender control of them for as long as the delegate is running for election and serving their terms. Voting for delegates. Normal users vote for delegates by appending zero value transaction output to their transaction, which uses the op return opcode followed by the opvote DG opcode, followed by the list of delegate IDs to vote for each transaction output. Votes cast by the transaction's inputs are destroyed, and votes are created with the new transaction outputs. The opvote DG opcode expects a simple list of delegates IDs, which one for which each transaction output, not counting the first transaction output, which contains this metadata, and the entirety of each transaction output's coin amount is used to vote for the delegate described by this array. Example. They give an example. Voting by delegates. Delegates vote by sending a transaction to special voting address. Use of this address makes it easy to account for how and when delegates vote. And this address has special rules as described in the special voting address section above. The transaction casting the vote does so by having a single transaction output that uses the op return opcode followed by the op DG vote opcode and the data describing the vote. Votes are described using a JSON object which is passed to the op DG vote opcode. Each key in the vote data object represents a ballot item, and each value indicates the vote itself. Each value in the vote data JSON object has a maximum size limit of 2 kilobytes, and the entire vote data object has a max size limit of 100 kilobytes. Even the 900 million coin supply and the 1 million minimum delegate registration stake, there can never be more than 900 delegates in the running, and therefore the map delegate state variable that holds voting information can never be more than approximately 90 megabytes. In practice, it ought to be an order of magnitude smaller. Explanation of keys and values. Key. The key is the JSON object. The key in this JSON object represents the ballot item for which this vote is being cast. Each time a transaction is sent to update the vote data, the update is considered incremental. It is applied on top of the existing vote data for that delegate, overriding any existing values for given keys. Setting a key's value to null will delete the key and the value, thereby withdrawing the vote. Value. This is the value of the vote being cast. The value can be no more than 2 kilobytes in size. New values for pre-existing keys will overwrite old value. To vote accounting and indexing. I suggest that anyone that is interested in this project read through this white paper themselves, because I'm pretty much reading the bulk of it here. But I would just suggest that anyone do that. Vote accounting and indexing. This voting system has been carefully designed to be efficient as possible, to add as little overhead on the blockchain and node processing requirements as possible, in order to facilitate the highest transactions per second rate possible. In addition to performance considerations, it is ideal to maintain full compatibility with all Bitcoin-related tools, so this voting system has been designed to maintain that backwards compatibility. Every vote cast, every stake made, and every delegate registration is performed via a TX output in the first output position, which allows the op return opcode followed by a new voting opcode that is unique to Flash, followed by the voting metadata. Any Bitcoin-based script interpreter will not parse the data following the op return opcode, but the Flash script parser will continue reading the script if there is a voting opcode immediately after the op return opcode, requiring that this voting metadata will be the first TX output position. Transaction output assures efficient lookups when discovering old votes that are being destroyed by new transaction outputs. It is also op return script parsing by skipping the parsing of any op return data that is not in the transaction output position. To facilitate accounting and indexing in the core code, some new variables and structs will be created: delegate class, map delegate state, vote state, pending state, map pending votes, pending votes by block. You're going to have to go through and check those out on your own. It won't make sense reading those out. Given a max coin supply of 900 million and minimum delegate registration stake amount of 1 million, there will never be more than 900 entries in the map delegate state variable. When a delegate reclaims their stake, their entry in the map delegate state will be deleted. Upon receiving a valid delegate registration transaction, each node will check to see if this new delegate ID already exists in the map delegate state, and will add a new struct if it does not exist. When receiving valid registration updates, each node will overwrite the given delegate ID's entry in map delegate state with the new struct if the new struct has a higher info version number than the existing entry. As each new block is accepted into the blockchain, each transaction in the block is checked for voting data in TX out, and if present will be validated and noted in the map pending votes and pending votes by block. Votes are not counted until the consensus height is reached or surpassed that transaction's block height. Every transaction has inputs and outputs, and any votes previously cast by the inputs must be subtracted from the map delegate state, and any votes cast by the outputs must be added. Each time the consensus height changes, which might happen with every new block, pending votes by block, is iterated, and each entry with a block height at or below the new consensus height is processed and removed from both the multi-map and the map. Processing pending votes by block means to fetch each transaction in the vector being processed, parse the voting metadata, and update map delegate state to count the new votes. If map delegate state is changed from processing the new consensus height, changes in all votes in the map delegate state are recounted, and the global vote state struct is updated to index the current active rule set. Future blocks will be validated against this updated rule set. In this way, a running total is maintained for all votes in map delegate state, updated with each consensus height changed, and the result of this vote is indexed in the struct vote state so that all parameters can be easily and efficiently looked up. Note: changes to the delegate's minor vote is processed instantly when received by node, but all other changes must wait for full finalization by allowing the consensus height to reach that vote's block. Calculating vote results. The keys in the vote data object are arbitrary. However, there are several keys which will be utilized by default when the Flash network is launched. Other keys will be ignored. Each vote and vote data can use a different method for determining the outcome of the vote, and that method is hard-coded in the Flash governance code. Here are explanations of the voting method for each of the vote data keys supported at launch. Vote height, minimum transaction fee, transaction for fee per B. Miners, Coinbase transaction and delegate signatures. Every block mine will have a Coinbase transaction with 0 output inputs. Similar to most Bitcoin-derived cryptocurrencies, however, Flash's Coinbase transaction will have a 0 value transaction out, 0 that uses the op return and op DG sign op codes as follows: opcode return op DG sign delegate ID delegate sig of block hash. This transaction out 0 is proof that the delegate ID was the creator of the block. Once every day, the Coinbase transaction will contain additional outputs to distribute the previous day's rewards to the miners and delegates. These rewards will be distributed as described in the miner delegate reward mechanics section above. As each day progresses and transaction fees are paid, those fees are burned. They are temporarily removed from the coin supply, and the first block of every day recreates those burned coins and redistributes them to the miners and delegates alike. Audit interface and URL. There will be new API command called get audit point, which can be used by the community to verify that this delegate is online with the blockchain that is in sync. This command takes no arguments. When users are choosing a delegate to vote for from that list, this list ought to show the sync state of each delegate so that the user has information to inform their vote. The response from the get audit point API call will follow the standard Bitcoin API format and might look like this. So you'll have to get into that. Getting down to the nitty gritty. Delegate interface, info interface. There will be a new API command called get delegate info, which returns a JSON object revealing information about every delegate, both elected and running. The results of this API command will be used for dashboard displays on the community websites and in the Qt wallet. This command has one optional argument, delegate ID. Specifying a delegate ID will filter the results to only return voting status for the specified delegate. Otherwise, data for all delegates will be returned. The data provided in this API command's response is derived from the map delegate state variable. This information can be used to see information about all the delegates, including which delegates are voting in which direction and how much influence, for example. Vote state interface. There will be a new API command called getVoteState, which returns a JSON object revealing the current state of all ballot items as a counter for the struck vote state variable. This is the law for the current block. Example given below. Check that out. FlashCoin.io, where you can read this white paper for yourself and go through this video as you read it. This API command and struck vote state are intended to only show the results of all votes of the previous block's closing, which makes these results the rule set that will be applied to the next block generated. If more details are needed about weights and delegates, then get delegate info API command should be used. Instead, voting interface, miner, and delegate statistics. Last two. Voting user interface, both the Qt wallet and the CLI will provide interfaces for voting. The wallets will have configuration parameters that can be set to control automated voting with the coins held in the wallet, as well as interfaces that show the current state of this wallet's voting power. Because votes are cast as coins are spent, not as they are held, the automated voting will allow the user to set a threshold level for the amount of coin in the wallet that is not voting as specified. And when the threshold is exceeded, the automation will send that coin back into the wallet with the correct voting preference set. The voting automation will be default combine all transactions into one output when resending to itself, unless the user has opted out of the transaction combining. Miner and delegate statistics. Data can be collected for both miners and delegates from their published audit URLs for monitoring how well they are synced. All delegates and miners should rapidly sync the current chain tip and maintain roughly identical mean pool transaction count. The audit URL provides a signed message showing this information from each delegate miner. Additional miner statistics can be collected from the blockchain itself by analyzing the Coinbase transaction to identify which miners are participating properly. Elected miners should never miss their block generation time slot unless the network is idling, and if a miner misses too high a percentage of their time slots, then they should be replaced with a more reliable miner. By gathering the necessary information and making it accessible to others, it becomes possible for the community to make informed decisions about delegate and miner elections, and well-informed decisions will lead to an optimally efficient network. So this is the FlashCoin Flash Go Faster white paper, which was released last year in 2018. And I think it's a very good white paper that, one of the better that I've read. And it's pretty thorough. Along with their website, also get over there and check out they have their roadmap on here. You get into a lot of projects and they don't have a lot of details about what they're up to. So these guys show you what they accomplished in the last year, and since they've been up and running, and they have the roadmap readily available for you to see what they're working on, exchanges they're working on getting on, exchanges they've gotten on, big news, things they're working on all over the world. So adoption in Africa, spreading economic freedom around the globe. So I'm very interested in these guys, and happy to have them as a sponsor of No Edits Crypto and my show. And everybody just go check them out and do your own research, but just read a little bit about what they're up to. Have a good night.